Okay, welcome back. So last time we discussed unique factorization domain. So let's briefly recall what all we discussed last time. A be an integral domain, then any A is called a unique factorization domain. If every element, non-zero, which is non-unit, can be written uniquely as a product of irreducibles. So any X can be written as product of irreducible, and this product is unique, essentially up to a unit. So if you want, like, you can multiply it by certain units. You can multiply it by u and u inverse, for example. But other than that, this thing is unique. So in the sense, more precise sense, if we write it as if we write x as p1 p2 pr for another expression of into product of irreducibles, then we must have that all these irreducibles are essentially the same. So then n has to be equal to r, and this pi's and qi's are have to be exactly the same, except for units. So they are associates. So they differ by pi and qr. Will only differ by units. So that was the result which is the definition. So every element can be written as a product of irreducibles, and this product is irreducible is unique up to associates. So if you have another decomposition, as I said, then pi and qi's are same, except maybe pi can be, and there might be rearrangement, and other than that, pi can be wi times qi, where each of these wi's are unique. Okay, so this is for uh, 1 less than I less than n. So r is equal to n, and each pi equal to, okay, so each pi equal to wi for some unit wi in a. So so first example was z, and that is called fundamental theorem of arithmetic, that every non-zero integer can be written uniquely as a product of prime numbers. And so that we know as fundamental theorem of arithmetic, that every non-zero integer can be written uniquely as a product of prime numbers up to sort of units. So, and then we saw that in UFD, every reducible element is a prime. And the proof was similar to how we proved in some of the other cases. We used unique factorization. So if AB can be written as product of, so suppose P divides AB and P is irreducible. So AB equal to some lambda times P. So then in one of the factorization, you write the factorization of A and factorization of B, and you write the factorization of lambda. P is a prime, so P is an irreducible. Sorry, P is an irreducible. So you write the factorization of lambda. So you have two factorization of AB, and one of the factor is P. So now even on the left hand side, when you have factorization of A or factorization of times factorization of B, P will appear there, because the factorization is unique. So P will be either in the factorization of A or in the factorization of B. So P will divide either A or P will divide either B. So P is a prime. So this is a check test for that if like in PID we have seen every irreducible is a prime. Same holds in UFD. Here also every irreducible is a prime. So for example, z dot minus 5. We have seen that it contains the irreducible 2, which is not a prime, because 2 divided 6, which is 1 plus root minus 5 into 1 minus root minus 5, but 2, none of those are divisible by 2, so 2 is not a prime, but it is an irreducible, so this ring is not a UFD. Then we proved that every PID is a UFD, and the way we proved it is so every non-zero non-unit you have to express into product of irreducibles. And for that, if it is reducible, then you write it as a product of two elements. None of them are unit. Then each one you can further continue to factor, and the fear is that might lead to an infinite chain. It may never stop. But because it's here, there we use the property of PID, And if there is a chain like that, you take the union of that chain, that is an ideal. And because it's a PID, it's a principal ideal. And by single element, so the chain stops. So it belongs to one of these stages, and there the chain stops. So it's a finite factorization into root series. Further, why it is unique? The factorization is always unique up to unit, because if there are two factorizations, then if there are two factorizations, then these are primes, because it's a PID. These irreducibles are primes, so these are two factorization into primes, and factorization into prime is always unique. So in fact, so Q1, for example, you take Q1 and P1, so Q1 divides this product, so Q1 divides one of them, so let's say P1. But then both of these are maximal ideals, because the PID non-zero prime ideal is maximal, so they have to be associates of each other. And like that, you proved it. We proved it. Okay, so next is so in particular, fx is UFD for any field f, because it's a PID. And next theorem we wanted to prove, so we'll not really prove it. We will give some, we stated it. If A is a UFD, then AX is a UFD. Okay, and before proving that, and in fact it is if and only if it's easy to see if AX is a UFD, then in particular A is also UFD. So for that, we define this field of fraction, or the quotient field of an integral domain. So let A be an integral domain, and you consider f tilde be AB. So field of fraction is, the idea is that this is the smallest field which contains this given given element, and contains this given integral domain, and any field which contains that integral domain will contain that field. So that's the quotient field. Like for Z, it's a quotient field or field of fractions is Q. So if you have a ring homomorphism from Z injective to a field, any field F, then F will contain Q. So there will be injective homomorphism from Q to F. And the construction was formal, so you define like Z cross Z minus 0, or more generally, if A is your integral domain, A cross A minus 0, you define AB to be equal to C. So you consider the pair AB to be A by B basically, and you define additional multiplication analogously, and that forms a field, and A to A mod 1. Inverse of A by B is B by A. If A is not equal to 0, 0 by A is the additive identity for any A and not equal to 0, and 1 by 1 is the multiplicative identity. And this is the formal thing. If you have A and if you have injective homomorphism to any field K, then this field, there will be unique field homomorphisms from this field to K, which compatible with the map A going to A by 1, the map phi. And this diagram will commute. So if you start from here, apply phi, then there will be unique map phi between F and K. We call it phi fk. Where it goes, it will take it to the same where you originally sent A by. Okay, so we'll not. So you can tentatively think this as like inverting just. So you have all non-zero element B in A, then you just attach 1 by B, then what you get is this. Okay, so intuitively you can think like that. This is the formal construction of the quotient field. So as I said, using this we want to discuss that A is a UFD, then AX is a UFD. I will not really give a proof, but we just give some basic definitions. We just use prove the basic lemma which is used. It's called due to Gauss and called Gauss lemma. Okay, so this we'll use later also. So I'll give you a complete proof of this lemma, and I'll just say using this you can prove the actual theorem. So let fx be a monic polynomial in Zx, and if fx equal to gx times hx for some, so fx is a monic polynomial in Zx, and fx equal to gx times hx for some monic polynomial gx and hx and qx. Then gx and hx both will belong to Zx actually. So this is the lemma. So fx is a monic polynomial in Zx, and fx splits as gx into hx for some monic polynomial gx and hx and qx. Then gx and hx actually both belongs to Zx. Okay. A general version of this is the following: if A is a UFD with so So fx, as I said, fx is a monic polynomial and fx splits into gx into hx. In qx, then already gx and hx are in zx. So if f is reducible, if it is a monic polynomial zx, and if it is reducible over qx, then it is already reducible over zx. That's what this says. So more generally, AB UFD with this field of fraction f, then if fx belongs to ax, fx is reducible over fx even without the monic condition, then it is reducible already over ax. Okay, so A is a UFD with this field of fraction f. Let fx belongs to, if fx is reducible in capital Fx, then it is already reducible in ax. If fx belongs to ax is monic and reducible, then it is irreducible, then it is irreducible over kx. Okay, so this is another thing we are going to use. How do you prove some polynomial is irreducible over ax? If it is monic and irreducible over, let's say you want to prove some polynomial is irreducible over qx and it's monic, then it's enough to prove it is irreducible over zx. Okay, so if it is monic and irreducible over zx, then it is irreducible over kx. Okay, so if fx is gx times hx for some monic polynomials, and then they are in qx, then so I'm going to prove this version, and the general version is also similar. Okay, so this is the general version. Okay, so this is the general version. So I'm going to prove the first version. Okay, so so you take a equal to z and fx is monic, and I have a factorization. So a equal to z and fx is monic, and fx belongs to zx, and it is monic. Then I want to prove that so that fx, and let fx equal to gx times hx, where gx and hx belongs to qx. Okay, so then I want to say that this gx and to show gx and hx are already in zx. Okay, that's what we have to show. So let n be the smallest integer such that n times gx is in zx. Okay, and m be the similarly smallest integer. So smallest positive integer. Positive integer, and m be the similarly m be the smallest positive integer. Integer such that m times hx is in zx. So basically, what you do, you write them in the lowest form, each of the coefficients, right? So the coefficient of gx a priori. So let's say gx is like a0 by b0 plus a1 by b1 x plus an by bn x. So you write in the lowest form such that ai and bi co-prime to each other, and you take the LCM of b0, b1, bn also, right? So something like that works. So that's what you have to do, right? So you take LCM of basically b0, b1, bn when they're written in the lowest form. So so then GC. So the point is, if you choose m and n in this way, then what is the GCD of the coefficient of n times gx? This will be equal to 1, right? So n times gx is a polynomial over zx. So n time gx. So let's say again n time. Let's say n time gx equal to a0 plus a1x plus anx to the power n, where these ai's are in or al, because these n's have no relation. So maybe n is not a good notation. So let's say it is of the form al x to the power l, ai is in z, right? So what is the GCD of this a0, a1, al, this coefficient? So I claim GCD of the coefficient is 1. If it is not 1, then something less than n would have worked, right? So this is because of, this is by, this is by the definition of, by the definition of n. Similarly, GCD of the coefficient of GCD of the coefficients of m times gx is also 1, right? Because you are sort of, n is the smallest, so this is smallest positive integer, and this is also the smallest positive integer, such that multiplying that it has integer coefficient. So now my claim is, so if you like, so claim mn equal to 1. Okay. So GCD of the n times gx equal to, okay, so maybe I should just, so let's say this, then just n times gx. So this is equal to, if you like, so definition of coefficient of this is equal to GCD of a0 up to al. So say this is equal to 1 by the definition of n. Similarly, GCD of coefficients of m times hx is also equal to 1. Okay. So claim is that mn equal to 1. So if there exists a prime, so I'm claiming mn equal to 1, that means m and n both are equal to 1. That means gx and hx are already in zx. If there is a prime such that the prime p such that p divides mn, then so then in z mod pzx, what happens? You look at z mod pzx, okay. So you look at in z mod pzx, in this ring, you have this identity, right? Mn fx equal to n times gx plus h times. So nm fx equal to this. And this was an integer coefficient. So p divides this. So this is equal to 0, right? And this is an integral domain. Z mod px zx is an ID So this implies n times gx and m times hx, right? So if you like, you can put a bar. You can put a bar everywhere. This is equal to 0 in z mod. Again, I'm repeating z mod p zx. But this is an integral domain, so implies that either n times gx bar equal to 0 in z mod p zx, or m times hx bar equal to 0 in z mod p zx, right? But that means p divides. So what is the meaning of 0? So all the coefficients. So all the coefficients of n times gx is divisible by p. So this is when we view it in z, right? That means that means GCD of the coefficients, GCD of coefficients of gx is not equal to 1, which is a contradiction. So why we have arrived at this contradiction? Because we assumed. So the claim is established. So claim is established, and Mn equal to 1. So there is no such prime P such that P divides Mn. Okay, so Mn equal to 1. That means M equal to 1 and N equal to 1, which implies that gx comma hx are already in zx. So this was the claim. If it is monic polynomial, and if it is monic polynomial, and if it is reducible in qx, then it is already reducible in zx. So that's what we have shown. And more generally, this is true for any unique factorization domain and its quotient field. And if fx is reducible, then and more generally, if fx belongs to ax is monic and irreducible, then it is irreducible over fx. So more generally, again, I'll repeat this. If there is a polynomial in zx you find which is monic and irreducible over zx, so let's say it doesn't have any, for example, integer root, then it is also irreducible over qx. Okay. So using this, we can prove that. Theorem that if if A is a UFD, if and only if AX is a UFD. So how is it entering the picture? Let me say just a few words. Okay, sorry. Let me just say a few words about it. So if A is a UFD, then AX is a UFD. And so if A, so proof some remark. So some remark on proof, not proof, some key points in proof. So if AX is a UFD, then every element can be, so this is easy. A is a UFD. This part is easy. So AX is a UFD implies that AX is an integral domain. So in particular, A is an integral domain. And every element of A is an element of AX, so it can be written uniquely as a product of irreducibles. Those irreducibles are in AX, but since it is in the element is in A, that has degree 0, a polynomial. So each of the factors will also have degree 0 because degree adds up. It's an integral domain. So degree of the polynomial adds up. So each of these factors are irreducible and they are degree 0. That means they are irreducible and they lie in A. So every element can be written as product of irreducibles. with of A can be written as product of irreducibles with those irreducible lying in A. And the composition is unique because the same holds in AX. So this part is easy. Second part is now that's where we are consider the quotient field K of A. Then Kx is a PID and hence UFD. Kx and hence a UFD. Okay, so maybe Kx, or maybe I have denoted by F, quotient field of fraction F of A. Then Fx is a PID and hence a UFD. Okay, and you have this canonical map from A to F. So Ax, you have a canonical injective map Ax to Fx, which like A I x to the power I, x to the power I, you send it to AI by 1, x to the power I, right? Uh, so here it is a PID you can write uniquely as a product of irreducibles. But the question is, so exactly that's why we discuss this Gauss lemma. So you have UFD and you have a polynomial. If that is irreducible, can you make it irreducible? Can you find a factorization where it is irreducible over AX? And with careful little bit of analysis, it's not hard. It can be done. So first, you can, without loss of generality, you can make the you can assume that the GCD of the coefficient is 1. So GCD makes sense even over UFD, as I'll discuss in a while. So you if you have A0 plus A1x plus ANX to the power n, a polynomial, then you write it as some B into A0 prime plus A1 prime x plus an prime x to the power n, such that GCD of A0 prime, A1 prime, an prime is equal to 1. And then you obtain a factorization over, you obtain a product into irreducibles over Qx, and then you adjust the denominator and you arrive factorization in Fx, and then you arrive at a factorization in Ax. And that that is where this version of Gauss lemma will be used. Okay, so I leave the details as left as exercise. Left as exercise. I might come back to it if we have more time later, but we are not going to use too much of it. So, so example. So anyway, we got if A is a UFD, if and only if AX is a UFD. So example, Z we know is a UFD, ZX is a UFD. Okay. And we have seen that ZX is not a PID. Not a PID. So for example, 2 comma x is not generated by fx in ZX. So this is not a PID. So there are UFDs which are not PIDs. Okay. So every PID is a UFD, but every UFD need not be PID. Okay. So every UFD, every PID is a UFD, but not the other way. Not every PID is a UFD. Okay. So, and for example, you can repeat this in ZX, you got UFD, you take ZX now, and ZXY will also be UFD, the polynomial ring. ZXY is defined to be ZX, and then the polynomial ring over that. Since ZX is a UFD, ZXY will also be UFD. And even these are not PIDs because you have two ideal X and Y and 2 comma x comma y, which is not singly generated, for example. And more generally, you take a field f, then fx is a PID. In particular, it's a UFD. So fx is a UFD, and then you have fxy polynomial ring in two variable. Then that is, since fx is a PID, is a UFD, so fxy is polynomial ring. It's the polynomial ring in variable y over the ring fx, and fx is a UFD, so fxy is also UFD. Polynomial ring in n variable is a UFD. So there are many examples of UFD which are not PID. So that's what I said. There are examples of, I've already said these UFDs which are not PIDs. And there are examples of integral domain which is not a UFD, as I've explained here. So z root minus 5 is an integral domain which is not a UFD. Okay. So we have this diagram among all rings. You have commutative rings here, right? So this is the all rings, this whole thing, let's say all rings. Then inside that you have commutative rings. In fact, in this course, we are only studying commutative rings. Then inside that you have integral domain. And our integral domain, we have found UFDs. So we just now gave example uh, of z root minus 5, which is an integral domain, which is not a UFD. So there are integral domains which are not UFD. Then, of course, not there are UFDs. Inside UFD, you have PID. Every PID is a UFD, but not other way. And inside PID, you have fields. So these are fields. PID, let's say, there's UFDs and integral domain like that. So as I said, we can define GCD and LCM. GCD and LCM of two elements in a UFD. So let x not equal to 0 be an x and y, or a and b be two elements in UFD. Then you write a equal to u times p1 to the power r1, pn to the power rn, where u and b equal to v times q1 to the power s1, q s to the power ql to the power sl, where u and v are units in A, and PIs are irreducible symbols in A, right? So in fact, so let's say you have P1, P2, Pn, and you can Q1, Q2, Ql, then you can make a bigger set uh, where you can combine both. I can write this as P1 to the power Rn, Pn to the power Rn, and Q times Q1 to the power S1, Q1 to the power 0, and QL to the power 0. And here I can have Q1 to the power S1, QL to the power SL, and then P1 to the power 0, and Pn to the power 0. So I can make the set of primes, common set of primes. And when whichever one is not appearing, I put them 0. So I can write simply as, so I can keep the indices same and the primes same. If some prime doesn't appear, then Pn to the power Sn, I can write that, and Rn, Sn belongs to n union 0. So they can be 0 or they can be positive. Then GCD of AB is nothing but P1 to the power minimum of R1, S1, P2 to the power minimum of R2, S2, and times Pn to the power minimum of Rn and Sn. This is the GCD, and LCM of AB will be P1 to the power max of R1, S1, P2 to the power max of R2 is 2, and Pn to the power max of Rn Sn. Then you can prove all usual properties of GCD, that if lambda divides A and lambda divides B, then lambda divides the GCD of AB and things like that. Similar property about LCM, and of course GCD of AB divides A and GCD of AB divides B, and if lambda is in A such that lambda divides A and lambda divides B, then this implies lambda will divide GCD of AB. So this definition of GCD is, and if you think about integers also, this definition matches. So check the definition matches with that of the GCD and LCM in Z. So this is the correct and general definition for, so maybe I should correct it, write it better handwriting. So if lambda belongs to a this is B, this is also looks B, and so and lambda divides A and lambda divides B, then this implies that lambda divides GCD of AB, and the usual properties are satisfied. Okay, so check that this is a good definition of GCD. Check the properties. So application. Okay. So let us end this thing by um, uh, slightly unrelated thing which we discussed, because we did a lot of theory. So let's do. We did a couple of lectures back the Wilson's theorem. Let's see an application of Wilson's theorem to end this lecture. So which of the following integers are divisible by 19? Okay. And similarly, which of the following integers are divisible by 17? So a bunch of integers. So let's start with this one. So 18 factorial minus 1. B is 18 factorial plus 1. C is 17 factorial minus 2. And D is 17 factorial plus 2. So what is Wilson's theorem? You recall Wilson's theorem. It says n minus 1 factorial is divisible by, n plus 1, n minus 1 factorial. So n minus 1 factorial is equal to minus 1 mod n if n is a prime. And in fact, it is if and only if. If and only if n is a prime. If n is not a prime, n is greater than 4, then this is 0 mod n. And if it is 4, then it is also not equal to minus 1 mod 4. Okay, so this was Wilson's theorem. And how do we apply it? So it's straight, 19 is a prime. So 19 minus 1 factorial plus 1 is divisible by 19. So this is true directly by Wilson's theorem. Now this one is, these two differ by 2. So this is false. Because if this is also divisible by 19, this is also divisible by 19, then that difference is 2. 2 will be divisible by 19. So similarly here, suppose this is divisible by 19. If 19 divides 17 factorial minus 2, so this implies, so if 17 factorial, So if 17 factorial is congruent to 2 mod 19, then you multiply both sides by 18, then you get 18 factorial is congruent to 36 mod 19, right? But 18 factorial is minus 1 mod 19, and 36 is so 36 you can 18 also you can think of as minus 1. This is minus 2 mod 19, right? So this is minus 2 mod 19, because 2 into minus 1 minus 2 mod 19, and this is equal to we have seen is minus 1 mod 19. This is not true. So similarly, you can prove that this is also false. This is also false. This is false. We multiplied both sides. If this is true, then you multiply both sides by 18. This side is 18 factorial, which is minus 1 mod 19. And this side I can, either way, 19 into 2 is 38. So this is minus 2 mod 19. Or you can say that 18 is minus 1, so minus 2 mod 19. So you get minus 1 is minus 2 mod 19, which is not possible. So this is false. And similarly, this one also, by multiplying 18, you can show this is false. There's another one, which of the following integers are divisible by 17? So very similar. So again, this is true because n factorial, so p minus 1 factorial is minus 1 mod p. So p minus n factorial plus p is divisible by p. This is directly by Wilson's theorem. Wilson's theorem. So if this is divisible by 2, then 16 factorial minus 1 minus 16 factorial plus 1 equal to minus 2. So if this is divisible by 17, we know this is divisible by 17, then this will imply minus 2 will be divisible by 17, which is not possible. So this is also a contradiction. So you subtract this and then you get this false, and similarly multiply by 16 to get a contradiction. So this is also false, and similarly this is also false to get a contradiction. Okay, so this is also not true. So only this one is correct, and only here the second one is true, and here also that second one is true. So this is a nice application of Wilson's theorem. So we discussed some. So today we discussed some properties of UFD, and we proved Gauss lemma, and we said by applying Gauss lemma we can prove that if A is a UFD, then AX is also UFD. And then we saw that all PIDs are UFD, but not all UFDs are PID, and all UFDs are integral domain, but not all integral domain are UFDs. And then we said that in a GCD and LCM can be defined in a unique factorization domain for two elements. And for Z, this is the usual definition of GCD. You can check. And we ended with after doing some theory, we ended with some exercise on this. Thank you.